Boyd, and I am. Oh, hey. Oh, that was a sound. Recording in progress. Hey, so really, like I was saying, I'm Dylan Ray Boyd, and I am super stoked to talk with you guys about the coolest ultra wideband active passive radar radiometer system this side and that side of the Mississippi, and that is my friends SWESARR, the snow water equivalent synthetic aperture radar and radiometer. Now, if you could see my face, and if you could see my screen, you guys can see my screen. If you've seen this screen before, chances are you've heard this talk before. Now, whenever HP was, making the rounds, dragging all of us out to make sure that we were here today, you can check those email receipts. I hid under the table because I knew I wasn't going to be able to change too terribly much this summer for this presentation. So I do apologize. If you would like to, you have my blessing to go out, get yourself a Coke Zero, and chill out for the next 45 minutes if you've heard this rattly voice before. But if not, hey, stick around, and hopefully we'll talk about something that I think is pretty gosh darn neat. Now, let me turn on my clock here to make sure that I'm telling myself right. So I want to try to give about a 35 minute presentation, and I'll leave about 10 minutes for us to potentially do some type of programming or maybe just a Q&A. We'll see how it shapes up whenever we get down on that timeline. But the three things that I want to go over with you guys today, if you haven't seen this talk before, I want to talk with you guys a little bit about SWESARR, let you know what it is and what it's up to. If you aren't familiar with active and passive microwave remote sensing, I know that we've got a wide range of backgrounds in the crowd today. There's a lot of people who know a lot more about radar than I do, and there's probably some people who have never looked at it and do not want to look at it. I want to try to make sure that we all got a baseline to at least sort of understand what we're all looking at here in this tutorial today. And of course, I want to give you guys some tools to poke around, play with this SWESARR data, visualize it, and when the time comes, hopefully get you in a position to start working with it and maybe turn out some journal papers together. All right, so we're going to get into it. If you come back to this tutorial, I don't know, 6 months from now, you finally think, okay, it's time to play with this stuff, but I don't remember anything that dude said. I want these 5 links up here to be there for you whenever you come back here. Now, what these 5 links are, we've got this top link, and this is the SWESARR pre-release FTP server that's hosted by Goddard Space Flight Center, if I'm not mistaken. And that is where I believe Batu, the principal investigator for SWESARR, is going to be churning out that SWESARR data before he puts it on NSIDC. So, there's some quality testing that you got to do before you get on NSIDC. So that's where the freshest stuff is, if you'd like to take a bite of it. Now, the SWESARR radiometer data, that requires separate processing, and that's already available on NSIDC for the Grand Mesa experiments, and you can click right there to check it out. Now, if you're sort of new to the snow game and you don't know about NSIDC, I popped a link in there. At one point, it was new to me, so I'm sure it's new to somebody. Next is the SWESARR Blogspot link. That is where Batu and the gang are posting information about what they're up to, what's next for SWESARR whenever they have time to update it. So check that out if you're interested, or send one of us an email if you're curious. And then lastly, I know that this presentation is being put on an Amazon server, and at some point those Amazon servers they're going to take a nap unless you put a coin in to continue. And so I've asked for some help, and I got a couple people to help me make a version of this repository that is tuned to run on your personal computer as best as you can. I know that installing all these Python libraries is a real big pain, but I tried to leave as much information for you to do that sort of thing as possible. So first up here, what is SWESARR, right? And I've got a link to a video of a video that was shown last year at Hack Week. But Batu sent me a couple slides last night. I'm going to see if I can share these. It looks like I'm sharing them to the right screen. So some slides about SWESARR. I think these are my slides about SWESARR. So I want to try to come back to this presentation a couple times just because he sent these to me about 7:30 last night. So he wanted you guys to get the down low on what's new with SWESARR. So if you haven't seen this picture before, if you haven't seen SWESARR before, I want you to know that SWESARR is a nifty little airborne instrument that measures radar and radiometer measurements simultaneously. In fact, that sucker measures 9 measurements at the same time. Now, what these measurements include are 3 frequencies for the radar channel. We have 9.65, 13.6, and 17.25 gigahertz at co and cross polarization. And the radiometer channels are measuring 3 frequencies at 10.65, 18.7, 36.5 gigahertz at H polarization. Now, this little crude doodle that I've made over here is trying to visualize for you that these measurements are all occurring at the same time. And what that means is that you have different footprints on the ground. So they're all measuring in the same location, but of course that wavelength is going to correspond to a different size measurement on the ground. We'll actually visualize that today, which is pretty cool. And if you aren't familiar with, what is he talking about with these frequencies and wavelengths, this isn't my cup of tea. Those correspond to a sort of physical, well, I shouldn't say physical, but an electrically equivalent sized wavelengths. And I visualized that over here at this bottom figure that we have here. This bottom line here is showing you the wavelength of this 9.65 gigahertz channel. It is about 30 millimeters. And this top line here is showing you that itty bittiest frequency, 36.5 gigahertz. It is about 10 millimeters down here. Now, this estimated maximum snow grain diameter size isn't actually, something that, HP or Megan went out and measured it at Grand Mesa, and they reported back that they found a big old snowflake that was about 5 millimeters or whatever's on here right now. This was me trying to estimate the limitations of a model I was using at the time. But regardless, this kind of gives you an indication of the sort of relative size of these frequencies to a particularly large snow grain, but I digress. So next up here, I want you to actually take a look at the instrument. Now, this is from that video of a video that I mentioned earlier. So you can check this out on YouTube. It's from the archive from SnowEx Hack Week 2021. But what we're looking at here is the actual SWESARR instrument. So this little guy right here, this little rectangle, I held that in my hand one day down at Goddard Space Flight Center. A fellow told me it was more money than I'd probably ever make in my lifetime, which was horrifying. And I quickly tried to put it back in the box. That is the ultra wideband antenna that SWESARR uses to measure all 9 of its measurements at once. Above that, we have our reflectors that sort of gathers other frequencies to channel to that antenna. And out to the side, all these big boxes, that's all of your microwave hardware that's actually doing the process of converting those measurements to something that we could store on a computer, analyze, and, correlate to snow measurements in the future. Now, Batu also has this nifty slide here that kind of more clearly shows what this is from a more modeled perspective. We still got that same antenna, and we still have that reflector, but he at least specifies, that front box is the radiometer system. We have a GPS unit. And I believe this is showing that on the back of the unit are our different SAR channels. So all of these guys are hooked up. They're poking out the side of the plane, and they are measuring all sorts of fun stuff. So if I could, I'd go back and add this stuff to this presentation. But it was, again, 7 o'clock last night, and I didn't want to stress anybody out or myself out. So I apologize. That'll just have to be in the video archive for now. All right. So this thing measures active and passive signals. So what exactly does that mean? If you don't know, I'm sure a lot of people here do, but let's just assume that we're starting from the basics. Now, whenever I first started learning about, microwave remote sensing, I really, really struggled with passive microwave remote sensing. I didn't understand what it meant. You'd open up a textbook, it would talk about some sort of Planck's constant and black body radiation and all sorts of scary words. But I eventually had somebody break it down for me a little bit like this. So if you were to look at your hands right now and sort of gaze upon those lines in your palm that that tell of your fate, that are tied to your future. If you were to do so, you would be directly emitting electromagnetic radiation into your eyes. Fear not, though. That's happening to you all the time. It's not some sort of deadly ionizing dose that you're injecting into yourself. You've got radiation coming from the air. You've got it coming from your feet, from the grass. It's all around you. And why is that? Well, the reason for that is that most mediums that we have out in the world consist of these things called atoms. And atoms will sometimes have charged particles in them. There tends to be a whole bunch of them. And if something is above 0 Kelvin, that means that those little charged particles are sort of wiggling about at different speeds. I try to visualize that here. So, if you have more thermal energy, these atoms are bouncing around a whole bunch. And since they're charged particles, they are disturbing the electric fields that they are resting in. If you have less thermal energy, they're going to be moving more slowly. So they're going to be disrupting that electric field a little bit less. And if you don't know, if you have a charged particle that's moving, it will induce an electric field, and that electric field will induce a magnetic field. And those things sort of go back and forth over and over, and you end up getting an electromagnetic wave that's propagating. And this is happening all the time, everywhere, naturally. And that's pretty cool. So, don't freak out. Don't go online and buy tons of shungite from a local retailer. I don't know if those things work. I really don't know what they are, but regardless, no need to panic. So let's see if I can zoom in a little bit. I don't like how itsy bitsy spider this guy's looking here. There we go. Here we go. So now I have this little visualization of a radiometer system. We've got a little horn antenna up top here with an antenna gain pattern. It's pointing towards the ground. And we see that it's measuring these little electric fields coming up from the atmosphere. It's coming from the snowpack. It's coming from the soil beneath it. And all of these signals are very, very weak. So whenever you're coming to measure all of this, you can't really do anything fancy like, ray tracing in video games. This is all really difficult to do. So typically what you do is you just say, oh, I'm looking at this certain area and I'm just going to, average what I'm seeing as a sort of total measurement. And we denote that as a brightness temperature measurement because it correlates to the physical temperature of the medium, because the physical temperature relates to how much, energy is coming to you. Now, one thing you do have to be careful about with these radiometer systems is if you have something called a side lobe, and that's where, you can't quite get your antenna pattern to focus all of its energy in one direction. You might be getting a little bit of something off the side here. I tried to visualize that here. It's not super relevant for this tutorial, but regardless, that's sort of the basics there. So if you only know one thing from this tutorial, I want you to know that you're measuring these naturally emitted signals and you're doing a little bit of averaging in order to see that stuff. All right. I would ask if there are any questions. I'm looking at the chat. I don't see if there's any questions. So if you have one, feel free to drop one. Unless you holler real big out there, I don't think I'm going to be able to hear you guys. So I'm going to keep on trucking if that's all right with y'all. Okay. So active systems. Instead of us measuring something that's naturally emitting from the environment, what we're doing here is we are sending out our own signal. And since we know what that signal looks like, since we know, maybe it's a chirp, maybe we've got it pulsing in some kind of weird, funky fashion, and we can control how much energy is inside that field that we're putting out into the world. This field is going to be real big. It's going to have some type of interactions, and hopefully, if you're if this is coming in the backscattering direction, you're going to be able to see that interaction with the environment. And because there's a whole lot of smart people that have been around since World War II, maybe before that, I'm not sure. There has been a rich history of people taking advantage of the fact that they know what signal they're sending out and using that to increase their resolution of what they're measuring. So to go back to what I said before, you could do some crazy processing with your range and your Doppler to do some kind of crazy sort of ray tracing sort of problems there to increase your resolution. And we'll be talking about that in just a minute whenever I show you some neat slides that Batu sent me last night. So we mentioned this beforehand of what SWESARR contains on the system, all of its frequencies, the different polarizations. This is a nice visualization of the plane that, or one of the planes that SWESARR has been flown on. It's sticking out of this little sort of cardboard looking portion of this window here. And there's another picture of the SWESARR unit itself. So it's in this little presentation here. So this image here was created by Ludwig Brucker. Real good guy. He worked on the radiometer side of this project for a while. And what he's visualizing here is, I think, something that Megan Mason showed yesterday. All these different snow pits that we have across the Grand Mesa. I believe there are 149 in this image right here. And what Ludo shows is that, you know, SWESARR got pretty good at covering all those different snow pits. So if you've got a snow pit and you want to correlate that to either the radar or radiometer measurements that were taken by SWESARR, you know, that's out there and available to you. Now, this last section here, before we get into the programming portion, is how to read these data sets. Now, I don't think that they are currently available in the SnowEx SQL library at the moment. I sort of piddled around with the GitHub page and didn't see it, and that's totally reasonable. You know, we don't have this on NSIDC in its SAR form, so I totally get it. Once that's out, I'm sure we'll collaborate and get it there. But for now, you'll have to suffer just a little bit with this little naming convention. And if I click this link here, it'll take you to the FTP server that's hosting all of these different files here. And this scares me. This scares me a whole bunch. So let me walk you through how this isn't as scary as it might look. So this first tag that we see here is the site name. In this case, it's corresponding to Grand Mesa. We've got this bearing angle, which corresponds to our flight direction. And since this is 275 from north, that is 0 north, 90 west is left east. And this is flying west at 5 degrees from west if we're going clockwise. And yeah, so that's what that's corresponding to. So you're flying a south line going west. Next up, of what's important to you guys, this line right here indicates the date that this was measured. So 2020 on February 11th. We've got our frequency, 9 gigahertz, and our look angle. This corresponds to a look angle of 45 degrees from the aircraft. Our polarization and some other little bits about the version number and all that. So that's what we have here. Now, we're about to get into the programming portion of this if you guys want to follow along. But I want to share a couple more slides just in case, you know, maybe you've seen this before, this presentation, and you're like, Dylan, you've already shown me all this stuff. Like, has nothing new gone on since you last showed up? My friend, that is not true. And I'm sure everybody on the SnowEx crew knows that to be the case. So what's up next for SWESARR? So SWESARR is, of course, going to be taking part in the SnowEx, I believe it's called the SnowEx 23 campaign, occurring this year and next year. So in our flights that are going to be going over Fairbanks, Alaska, and sort of that way northern portion of Alaska that did not have a name on Google Maps whenever I was looking at it last night, we've got all of these top-notch names that SWESARR is going to be flying over, you know, Caribou Poker Creek and Bonanza Creek over here in Fairbanks and over here in the coastal plains. So SWESARR is going to be taking a whole bunch of measurements very, very soon in the near future. I believe these flights are scheduled for October, November for the snow off sites. Anyway, so that's coming up next. And if you've paid attention to the 2020 data set, you might know that there is a reason why it hasn't been put onto NSIDC yet. Now, if we look at this image here that I have on the left, you can sort of make out two images here. We have this back map that's indicating the underlying vegetation of our surface, and overlaying it is one of our SWESARR images. And you can see that this forest is not sitting right on top there. There's about a 100-meter offset on portions of the image. It's not consistent for the entire image. And this is just a particularly bad example further down on one of these cross lines here. Well, Batu heard the cry of the people and said that he would not stand for this. And what we see over here on the right is an updated algorithm that he's been working on with a few folks. I believe this on the left was an automated algorithm that he made called, he didn't make the algorithm necessarily, but he used an extended chirp search algorithm, if I'm not mistaken, to sort of automatically do all this process. And instead The updated algorithm is using a time domain back projection algorithm. And you can see here these roads that are across the mesa and how they connect into the SWESARR image down below. The geolocation area has been greatly minimized. I think that he ran the numbers and found that it was within 6 meters of accuracy compared to what you see over here. So Batu's getting that out as soon as he possibly can for the 2020 data. So hold on tight if that's what you're waiting for. And we've got a couple more images here for what he's been working on with this. You can see here that this is a Radiohead said it wrong. It's not RBG, RGB image here of the of the SWESARR flight over Grand Mesa. You can make out these tiny itty bitty little pixels here, and he's got these labeled as CR. And you know, you can scratch your head for a minute and go, those are corner reflectors. And so these bright little pixels are looking like we'd expect here. This here is I believe a single look complex image. If you can understand this image, you know, more power to you, my friend. This is a little bit beyond my pay grade at the moment, but that is sort of indicating the resolution of our SWESARR instrument at the moment. We can kind of touch base back on that later if we're interested. I'm going to skip ahead for time's sake. Now, these last images are just some examples that he's showing here for the updated algorithm as well. So I just wanted to let you guys know these images are not available on the FTP server yet. We're currently working on them, but you know, you guys are here to listen to me yabber about SWESARR, and I just wanted to make sure that you guys were taken care of so that you knew what was going on. So I'm going to take a second. Has anybody in the chat said nothing? It looks to be the case. All right. I'm going to wait because I can't quite hear anybody. I'm going to wait 10 seconds for dramatic pause, and we're going to continue.
Can you, Can you hear me, Dylan?
Yeah, I can. What's going on?
Yeah, we have a raptured audience here listening. Any questions for Dylan?
I feel like I'm losing my mind in here. I'm just sort of you know, I do it every day. I talk to myself like a maniac every day, but it's very.
We do have one question for you, Dylan.
Yeah, sure.
Hey, Dylan, it's Jack.
Hey.
Just thinking forward to Alaska, do you think everything will be settled for the geolocation as you move up there with the new algorithm, and like it will be a much faster data production moving forward?
I do believe that the errors that were caused in the 2020 measurements, I believe that was because of an error that was on board the system. I think that the timing, one of the timing units for the SWESARR instrument had a malfunction during the flight. And that's been a big headache that Batu's been dealing with to try to fix this. Because I mean, if you don't know when you took a measurement, you know, how do you, correct this down to the microsecond or, less to get that geolocation corrected? You know, light travels real fast, my friend. And I believe that was the big error. So I don't think that Batu is going to be having an issue with processing this data in the future. No, thankfully. Of course, something else could break, but we're working our hardest to make sure that doesn't happen.
Any other questions for Dylan? All right, and Dylan, could you zoom in again to make your text a little bigger there on that?
Oh yeah.
Thanks.
Let me see here. I'm using that Windows plus key here to do that. So let me see if I can set that to 200 and see if that helps. How's that, guys? All right.
Yeah, that's
maybe
great.
Well, let me ask this. Would it be better if I just did it from the let me check here. Would it be better if I did it from this site? If I zoom in here, would you guys like that better?
That looks better to me, actually.
Yeah, we got these table of contents here hanging out with us on the side, but if you guys can read that better, I mean, this is the important part to read, right? The actual code. So I definitely don't mind chilling on this website with you guys. All right. So if Anthony's giving me a thumbs up, you know what? I trust that man. So I'm going to roll with it until somebody hollers and says, please stop. So, all right, guys. So if you want to follow along on one of the servers that are available to you, you can run this on the cheapest itty bittiest of computational clusters that the SnowEx Hack Week community or team has purchased. I tried to make this as lightweight as possible. What we have here are all of our imports for visualizing our SAR data. This little line of code that we have up top here is, I put this in because I'm using CartoPy, and I had an error that I ended up having to use this speed ups disable to get this running on my Windows machine. So that's what's sitting up here. We have this import request library to handle downloading the data from that FTP server for us. And that's going to be the big bottleneck for running this code if you want to follow along. I'll talk about that in just a second. We have raster IO that's going to be used to help us sort of manage our raster data. Don't worry, I've got some functions so that you don't really got to stress yourself out about that. GDAL, when are you not going to be using GDAL in this type of work, right? CartoPy is going to be handling some coordinate system conversions for us. We're going to be feeding in some latitude and longitude values, and we got to convert that to that crazy coordinate system that they're using that is like meters from some sort of state border or what have you. So this CartoPy, he's doing all that hard work for us. RIO X-ray. And X-ray, if you aren't familiar, X-ray, you can sort of think of that as an in-dimensional pandas data frame, if you will, or maybe just an in-dimensional MATLAB matrix. You can have like a four-dimensional matrix in MATLAB, right? So this RIO X-ray is just there to give us some nice raster image support for that. And we got some nice little plotting tools down here that we're going to be working with, right? I think there have been previous tutorials on HVplot. Maybe I'm the first up this year that's using it. I'm not sure. But regardless, the rest of this is setting up some directories that I think are already on the GitHub. So if you clone this, you've already got these two. But these two lines here are what are generating those. So if you run this should just be importing all that stuff. I've tested it on my little computer and on the server, so it should be working good. Now, next up, we're going to be setting up our ability to download the data. So if you go back to that little picture that I had earlier for selecting your data, all we're doing right now is we're navigating that FTP server. So here I'm selecting a cross line that was measured on February 11th, 2020. And inside that folder, there are 6 measurements. And with the power of the little, oh Lord, what do you call that? Those little one-line for loops, that crazy list comprehension that Python does, that's the word. We're going to use that to prepare the output directories and the position on the website to download all our files. So this one is the links on the website, and the output paths here is the links on your current computer where those files are going to be stored. So if you run that guy, hopefully, if this directory is created manually from this, it'll give you a little heads up that that's what happened. If not, this little try statement, he's just there to let you know that, hey, you've already run this before and we're ready to roll. So this guy is the line that actually downloads that SAR data for SWESARR. Now, this is going to take you a minute to run. It takes about, when I last ran it runs about 2 minutes. It kind of makes you sweat a little bit thinking, oh no, is something broken here? But that's because, raster files are pretty large. I didn't want to shove that onto the GitHub, 6 files that are 65 megabytes each. That would be very rude of me. So for the sake of this tutorial, I asked that if you want to try to follow along, this is the one that you don't want to waste too much time on not clicking. So that would be my suggestion there. So for the sake of the tutorial, I'm just going to assume that I've already run through this to just sort of have things run along. Now, this next line here is this file this function that I wrote called join files. And what this is doing is it's getting those SAR files that you've downloaded, and it's shoving them all into a big X-array for you to take a look at here. That's sort of tedious. I probably didn't write it in the most efficient way, but it's there for you to use if you'd like to sort of build upon that. I'd love to see somebody take that and maybe make it more efficient. But this is what we have here after running our sort of combination or combining function for this data. So we have this 3-dimensional data unit. This 3,959 and 4289 number correspond to the pixel coordinates of our image. And this 6 corresponds to the 6 SAR measurements that we've taken. So you can see here that this band that I've designated, we've got 9 VV, so that's 9 gigahertz, VV polarization, 9 VH. You get the idea, so on and so forth. And these XY values show you the position along the mesa for you. And so that is our little X-ray. Now, HVplot is a nifty little plotting tool that lets you take raster data and visualize it within Python pretty easily. What this function's doing, it's all right here. So we have hvplot.image for our data set here. And we're using this little tool called group by band. And what it's doing is it's saying, you know, you've got these 6 slices. I'm going to give you a drop down for that to visualize all this. These values up here are just, you know, color limit. We want to look at values between -20 and +20 dB. Our color map is gray. Our coordinate system is this UTM zone 12N. This was for last year. It seems like they updated it, so it has to be just a 12 now. But regardless, we're looking at this back image here of Esri imagery, and this is what the output looks like. It's very handy. I'm pretty sure you guys have seen this before. You know, you can mouse over it and look at it that way. I'm going to zoom out just a little bit because, need to go back up. Now, if this was in view, you could see that there's a drop down where we can take a look at these different values. We're currently looking at 9 VV, and I told you earlier about that footprint, right? So we have that 9 gigahertz VV polarization. If I switch to 17 VV, I'm actually not sure if this is going to update on this website. So I'm going to go back over here and do that update. So we see the size of the footprint here. And if I update that from this side, drum roll, please, it should skinny up. Maybe it's a sleepy server today. I apologize, boys and girls. It looks like she's a sleepy little person here. So we're just going to truck along. But if you can believe me, if you can get this running on your side, I do promise that in fact does work. However, I'm live, which means we're cursed here. I apologize. So in theory, if that worked, and if you got a big smile on your face from it working, you know, congratulations. You've got some tools in your toolkit for, you know, manipulating raster data, plotting it with HVplot. I think it's real nifty. Now, I'm going to move on to the radiometer data just to kind of keep trucking along. It looks like I've been talking for 30 minutes, and I should probably hurry up so that you guys can stop being tortured by my voice. Radiometer data, right? So this is much simpler than raster data because, man, we're just looking at a CSV file, comma separated values, right? So we can just use something like pandas to plot all of our data here. So we're still going to be using HVplot and the HVplot pandas extension to get our data here. And I point out here again that I don't think that this data is available on SnowEx SQL at the moment, but I'm sure if you guys hoop and holler, you could probably get it on there. You could annoy somebody to get this stuff. It's on NSIDC, but I also understand wanting to wait for both the SAR and radiometer buddies to gather on the SnowEx SQL Amazon server. You know, let them walk down together. But assuming that we don't have that at the moment, you're probably going to need to download it yourself. So I have this little tutorial here for using wget, and I have 2 functions down here. You know, 2 command line prompts. These are just tutorials for, you know, if you're on Windows, how to get wget working. If you're on Linux, you probably already got it. So, you know, just go to town, my friend. Now, Scott Henderson wrote this line last year, and it did work last year. But I think NSIDC said, you know, I think we want to beef up our security. So I think they force you to put in a username and password here. So if you got a NASA Earth Data login account, that's where you're going to put in your username and password. And I was real careful to not put in my username and password here. So anyway, just uncomment this line, give it a run if you'd like, but don't worry. These radiometer files, they're only about 100 kilobytes. So I said, why not? We'll just go ahead and put that on the GitHub page just as an example file. So that's what we have right here. So I'm pointing to this example SwesARR radiometer file that we have on our server. And we're just using that nifty little pandas read CSV file to pop it in here. And we'll use this radiom.head because, you know, we've assigned this variable of this pandas data frame to radiometer. We'll use this to just show the top of the table so that we can take a look at all the variables that are inside this without having to open up, you know, Notepad or Excel or something other that's not as cool as, you know, Python. Anyway, so we have our timestamp for when this measurement was taken. We've got our latitude and longitude values showing the position of this radiometer measurement. Our elevation, I believe from the aircraft. I believe that's what it is. No. I believe that's the DEM, and we have the antenna altitude showing the position of the aircraft relative to the DEM over here. And in the middle, this is the bread and butter of why you're using this, right? These are the brightness temperature values denoted by T. If this was in LaTeX or LaTeX, T underscore B. Now we got our brightness temperatures, TBX, TBK, and TBKA, corresponding to the 10, 18, and roughly 36 gigahertz measurements. And that's all throughout this file here. So that's what these guys look like. All right. So we're going to finish up with one slightly silly thing on plotting this. Now, if there's a more efficient way of plotting this, I will gladly heed the lectures of those wiser than I. To get this plotting, I ended up making two variables. I have a radiom variable here, and I also have a radiom p for plotting. And the reason for that is we have these three measurements, and to get these plotting with the longitude and latitude values, I think I had to pair each of those measurements with these values, even though they're identical across here. So I had to duplicate these values 3 times in order to get this plotting with pandas. Not super efficient, but I still like HV plot, so that's what I wanted to do. So we have this radion p dot HV plot dot points. So the last one was image for the raster image, and now we're using our points image to get this going. This group by ID, if we scroll up just a little bit, I believe we have right here, ID series right here. Yeah, so our ID corresponds to this line right here, which is our X band, K band, and KA band of variables here, which again correspond to these values. And that lets you use this little drop down here to alternate between these guys. And again, I'm a cursed man today, and this server sleeps quietly as I toil beneath its weight. Regardless, you got this going for you guys. At least this little HTML friend of ours is showing you all these nice little values from the drop down, which is very handy. And I've got one more a section here. I started this presentation off saying, man, this measures SAR and radiometer at the same time, and it would be foolish of me not to give you the opportunity to plot those at the same time. And we've got that here. I've written a function that does that tedious work that I had up here for the radiometer stuff. And I, panned it out for the entire SAR and radiometer data set. And we have that down here. So you can use that function if you like. Now, I will say that whatever the bounds are for the image, it always makes a negative version of it. I'm not sure if that's if it's an issue with HV plot or if it's something that I did. I definitely didn't insert a negative value in here from what my memory tells me, but I did want to throw that out here. So if I were able to switch to KA band, it would be showing brightness temperature values at negative 250 Kelvin, which is a horrifying physical concept to even remotely consider. But regardless, so this guy's here for you. So it looks like the timer's telling me I've been talking for at least 37 minutes. Oh, hey, is somebody wanting to say something? No?
Continue.
Okay, sure, yeah. So I had a little exercise here if you guys wanted to partake in it, or if you guys just want to sort of chill out, talk about SWESARR, I'm down for that too. If you want, I've given you some tools here. I've got this join SAR radiom function here, and I've got this output. If you'd like, I think it'd be pretty fun to sort of plot things as a time series visualization for both the SAR data and the radiometer data. And yeah, I would highly recommend using the data series if you'd like. I can give you all some time if you guys want to do that. If that's not your cup of tea, we can definitely just mosey along. But anyway, that's about the sum of my presentation here, right? So I apologize. It was I had to compress last year's presentation into 15 minutes, and you guys gave me free room to talk for a whole 45 minutes, and I think I've used up 40 of that. So I really appreciate your patience and suffering through this with me. So yeah, I apologize. If I had more time, I really would have loved to try to integrate this this exercise more cleanly into the total tutorial, so I wasn't just talking for a solid 40 minutes. But anyway, man, I can't stick a landing. I can't say just thank you to everybody. So anyway, guys, thanks. Yeah. I want to give a big thanks to Scott Henderson and Joachim for helping me get this on the GitHub. I don't know. I mean, I know I was very inept last year, but my goodness, I spent 2 weeks like wrestling a YAML file, and if Joachim didn't step in, this would not be on the website. I apologize. That was rough. So thank you both of you for everything you've done for this. So anyway,
thank you. Thanks so much, Dylan. That was really, really good. Awesome overview of a pretty complicated instrument package with lots of opportunity for data fusion there. So thanks for that. Really well done tutorial.
Appreciate it.
I think maybe with the time we have allotted, we'll maybe have just a couple questions and have that great exercise you planned out for people to do on their own, and maybe reach out to you with questions over Slack.
Yeah, that'll work. I mean, I just ended up using matplotlib to make a line plot. And I'm pretty confident everybody in this room can plot a line somehow. So, but I mean, if you're struggling, definitely feel free to reach out because I struggle anytime I use Python at all. So I understand that.
Great. Thank you, Dylan. We do have a question from the audience.
Yeah, sure. Ooh, is someone talking to me, or I apologize.
Sorry, Dylan. I'm just moving a microphone. Hang on.
No, it's all good. I just heard the whispers of a ghost from far off in the yonder.
In the select data section, you wrote 6 file names there. So if we have a lot of data sets, do we need to write all of them over there?
Are you talking about in this function right here?
Yeah, exactly.
Yes. So this is a sort of template that I've made to sort of download data in mass. Now, I would recommend that if you're just trying to get this data on your computer, I think, yeah, look at me from 2021. I would really recommend just using a good old wget function, or not function, but a wget call. And I would copy and paste this guy into the command line if you just want to get, all that data down. Because you can just tell it, hey, if it's got a TIFF on the end of it, give it to me. I'm not sure if that's exactly what you're asking, or if you're saying that you would like to have more control over your query.
I think you answered the question. That was great.
Okay, great.
Any other questions from the audience about SWESARR?
Yeah.
Got one in the back. I'm gonna just run around with the microphone.
So this is less of a question and more, I wanted to give everyone a heads up that the NSIDC's server is currently down. So if you're trying to use that wget command, it's not going to be working for you right now. We're working on it, and I will update when it's up again.
Yes.
Thank you. Thank you very much.
So that would be, let me check here. Where did I put it? That would be this wget command that's talking to NSIDC. The one that I showed over here for the SWESARR data that I think is hosted on Goddard Space Flight Center right here. That one should still work. So also want to make that clarification. So there's 2 wget commands that you can sort of find in here.
Great. And one just real quick question, Dylan.
Yeah.
On your example image, if you look cross track on the image, which part of that data would you be the most confident in? It looks like on the sort of western edge, it gets really, really, really low, and then it gets high right before you go into maybe the data that you would be most confident in. Can you just comment on that?
Yeah, absolutely. So whenever Batu put this out, he said that, I told people what the swath size was, and this is a pre-release data, and he included information that was larger than his area of confidence. So the center of this image is where everything is supposed to be the most accurate. And as you get along the edges, you're out of bounds for the validity of his algorithm that he used to convert those radar measurements to, those raw measurements to radar measurements, right? And that's one thing that we sort of struggled with was, if you just have a simple Python file, what is the center of this line, of this flight line, right? But yeah, if you're working with this data by hand, maybe in QGIS or something, try to stick to the center of this total image here. Can I zoom in to sort of look at that? Come on, let me in, man. Hey, yeah, there we go. So yeah. So the center of this image for sure is the area of highest confidence. But like I said early in the presentation, I think that this new updated image, I'd have to double check with Batu. It looks to me like it's been clipped so that you don't have that weird stuff on the outer edge. I'm thinking that whenever he releases this new image, that you won't have to worry so much about, hey, there's a weird drop off randomly on the far left side, right?
Yeah. Okay, that's great. So
Yeah.
for today's purposes, we'll stick to the
Yes.
center. For folks within Hack Week working with
Yes,
this data, that's great.
exactly.
Thank you.
Right. Sorry about that. I'm talking.
Awesome. Well, let's thank Dylan for a great presentation.
Thank you.
Okay, we've got one more tutorial before we break for lunch. If everybody wants to stand up for a second, just stretch the legs a little bit, and we'll sit back down and get started as we get Naheem set up here, and I'll introduce him in just a second.